Hello, this is Jason Kendall, and welcome to another one of my introductory astronomy lectures. Okay, last time we introduced the concept of special relativity, which said that the inertial reference frames are equal for everyone so long as you are in one. So if you're in an inertial reference frame, you can't tell one inertial reference frame from another by any means, except that they might be moving relative to each other. That's the only thing. Now, inertial reference frames can't be accelerating with respect to each other. They can't be decelerating. They can't be rotating. They're simply moving uniformly at a uniform speed, or they're standing still. That's the essence of an inertial reference frame. And we found that there were some implications for that, given that everyone measures the same speed for the speed of light. The speed of light is a constant no matter who measures it. That is the other axiom of special relativity. So this has implications. One of the implications is that moving clocks are out of sync with clocks in the direction that are ahead in the reference frame that's being observed, being out of sync with respect to clocks that are across the entire reference frame that you're watching go by. The next one is, if you're watching an inertial reference frame or measuring the clocks of an inertial reference frame as it's moving by, those clocks seem to be moving slower. And third, if you're watching an inertial reference frame, measuring what you see inside that frame as it moves by, you see that the entire reference frame appears to be shortened in the direction of motion. And this is all due to the constancy of the speed of light. No matter what the speed of light is, it is what it is, and therefore you never measure it adding or subtracting onto any other speed. The movement of an inertial reference frame does not add to the speed of light, nor does something moving inside of an inertial reference frame add or subtract from the speed of light. The speed of light is always a constant, no matter who observes it. That's a universally bizarre statement. So, and what's funny thing is about this particular statement is that it's a measurable thing. So we can measure it. And in fact, special relativity, I'm just going to lead in really here because this is a bizarre concept, is that special relativity is so incredibly well studied and well measured that we no longer measure the speed of light. It is simply defined. The speed of light is defined as a conversion factor between distance and time. So we actually define the unit of distance based on the unit of time. And by using because special relativity is seen to be so completely true. So we'll describe some of the experiments that show that in a second. So once again, special relativity is not a trick. You don't change reference frames and then all of a sudden, oh, it's gone. These effects are gone. They're not tricks. They're not tricks of the eye. They're not ghosts. They're real effects. And they're real effects of measurement. And so one of the important things is that we no longer have simultaneity. We no longer have absolute space. We no longer have absolute time. Time is simply the thing that you measure on a local clock. So that local clock is that thing that tells us time in our inertial frame. All right, so what do we mean by syncing clocks? Let's see what we mean by that. So let's look at those three things in general. Moving clocks are out of sync. Great. All right, so how can we define what we mean by clocks that are in sync? All right, so imagine in this room, I've set up a whole bunch of clocks. Some of them are hanging by the ceiling, some of them are on tables, some are on chairs, some are on the floor, some are on the walls, and they're everywhere. And I want to make sure they're all in sync so that when they go off at noon and they do their alarms, they go off at exactly the same time. They give 12 chimes and then stop. So that's my goal. So how would I do that? All right, so I would start by making one of my clocks a reference clock. And I'd say, okay, this is my reference clock and it's ticking. So then first things first, I make sure that every one of the other clocks is ticking at the same speed. That's good because maybe I wound them up too tight or maybe they're defective or something. And I just get rid of the clocks that don't go at the same speed. So inside of my inertial reference frame, I have a whole bunch of clocks that tick at the same speed, at the same rate. So I hear this tick, 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 and make sure it's a nice big tick like a grandfather clock so they all make a ticking sound, not digital things so that don't make any sounds. Although I could do that, but digital clocks that beep are really irritating. So we don't use those. We're just going to use like these mechanical watches because they look cool. So, all right, so we got mechanical tickings that occur and we can hear the ticks because maybe there's 100 of them in the room. So how do I make sure they're in sync? Well, I go to a particular clock that might be this one on the far wall, and I have the clocks now have the ability to link with each other. And how do they link with each other? Well, they say, I lay down a series of meter sticks, and they say, okay, Mr. Clock, these are smart clocks, they're mechanical, but they're smart. So I lay down a meter stick between them and say, okay, from this clock to that clock is exactly 2 meters. Great. So now the master clock knows that when it sends a signal, the far clock is exactly 2 meters away. And then that far clock is going to take that signal and immediately respond that it got the signal. So we can know how long maybe because they all run at the same rate, we know how long it takes the clocks to respond because they're all made by the same manufacturer or something like that. And we test that, so we know that they respond at the same rate. So we can take that into account. So the clock sends a signal, it processes the signal and sends the signal back. So from that round trip time, we can determine whether or not a clock is in sync or not. And so if it's out of sync, we send another pulse, and we do that to all of them everywhere in the room. And so the master clock then can determine whether or not every single clock in the room is exactly synced with it. Because as it sends a signal out, it knows maybe that one's 5 meters away. Maybe this one's a half a meter away. Maybe this one's right next to it. Maybe there's one's 20 meters away. It's a big room. So let's say they're all now in sync. So we've got a lattice of clocks on the walls, on the floors, on the tables, on the chairs that all are in sync. Now, I take this box, this room, this inertial frame, and I move it. I get it moving. It's now moving at half the speed of light that way. What does a person outside see? All right, so a person outside is watching this zoom by. Here we go, all the things moving by. So as they move by, maybe the master clock still has to try to keep all of them in sync. So it's going to do that. It's going to try to keep all of them in sync. So what it'll do is it'll send out a signal, and that signal then gets responded to. And the pulse of the signal from the master clock spreads out at the speed of light and gets intercepted by the clocks, and then they respond. So inside of the clock, because we always have to stay in sync. So let's just reduce it down to 3. So we got 3 clocks, 1 in the middle and 2 on each end. So in the reference frame that's moving, it's scooting along. We don't know that it's moving because we're at rest inside of an inertial reference frame. So the clocks then just ping back and forth, and they're just pinging back and forth nicely like this. Ping, ping, ack, ping, ack, ping, ack. That's what they're doing. So, but what does somebody see that the clocks are moving by? Well, since the speed of light is constant, remember, this is like a light pulse. It's going out at the speed of light and coming back at the speed of light. So what does somebody see that's going by? Well, the clocks leave the signal behind a little bit or catch up to the signal. So if the clocks are here and then they're here, the signal simply spreads out from the place it started. So the first clock to encounter the signal is the one trailing. So it sends its response back. And the other clock that's going this way, and it sets its time as soon as it gets the signal. It doesn't wait to send the clock signal back. But then the second one, which is in the lead, has to wait a little bit because it's rushing away from the signal, according to someone outside. So therefore, the clocks in the lead are a little bit behind the clocks that are trailing, because the clocks that are trailing catch up to the signal, and the clocks that are leading are rushing away from the signal. And the signal starts from here and expands outward, not from the signal source doesn't rush with it. The signal source, according to an outside observer, starts there and rushes outward. So therefore, the clocks, according to an observer watching from the outside, seem to be out of sync. That's interesting. That's our first thing. And we can think about it even a rocket ship. So you can have 3 rocket ships in a row and they ping back and forth. So the 3 rocket ships then their clocks out of sync. They're not even physically associated with each other. They just simply are flying in formation at exactly the same distance so that the ping back and forth occurs. The 3 clocks in the 3 moving spaceships will appear to be out of sync as they zoom by, if they're zooming by at very fast speeds. All right. So the next one is that moving clocks themselves appear to be moving slower. All right, well, not even appear, they do move slower, according to someone watching them. So I'm watching a moving clock. I make my room a place where clocks are working. But now I'm going to make a really special clock. I'm going to make my inertial frame extremely large. Let's make it just gargantuanly big. Let's make it out to the moon. Moon is about 200,000 miles away, roughly a little bit bigger than 186,000 miles. And you'll see why I'm going to use that in a second. But let's say we've got a really big room. And this really tall room, I don't care about it as being big, I care about it being tall. And so inside of this tall inertial reference frame that's moving by at a very fast rate, all I have is something that creates a signal, it makes a flash at the bottom of the clock, and that flash moves straight up the column and reflects off a mirror and comes all the way back down. And I'll call that a light clock. So it will only flash again when it gets the signal for the previous flash. So it goes flash, bounce, flash, flash, bounce, flash, flash, bounce, flash. And really we only care about one flash, but that's okay. Because the speed, remember the flash of light that's inside the clock moves at the speed of light, according to everyone. Not just me, but to everyone. The speed of light of the flash, no matter who measures it, always goes at the speed of light. Great. So now we've got this tube that's 186,000 miles long that has a mirror at the top and a big flashy bulb at the bottom, and the light stays inside of the tube. It doesn't go outside the tube. It can't leave the tube. It's inside the tube. So and we know that it hits the top of the tube because that thing like turns a red light green or something silly. And it turns at the bottom, it turns a red light green as soon as it signals. So we can know when the flash hits the bottom and hits the top. Okay, so I see that it ticks once per every other second. Remember, it's 186,000 miles long, so it flashes, ticks, and goes there. So it is a 2-second round trip. I could cut that in half, but I like the idea of going to the moon and back in a second and a half. So in 2 seconds. So we have a tube. It goes up and down inside of 2 seconds. Let's cut it in half so it's 1 second long. 1 light second long. Well, it's a light second long, light second high tube. So how fast is it now moving? Let's take the tube and now with the entire room, and it's moving to the left at, say, half the speed of light. All right, so what does an outside observer see? First, the light pulse never leaves the tube. It can't leave the tube. It doesn't leave the tube. It stays inside the tube. So we're all in the tubes together. It's not going down the tubes, it's going up the tube. All right, so the light pulse stays in the tube. So as it moves, it appears from our perspective, watching the tube go by. So inside, we just watch the thing go up and down and up and down. But outside, we see it go at an angle. We see the light pulse go at an angle because as the tube moves, the light pulse stays inside the tube. Interesting. So let's say it's going half the speed of light. Well, now you've got an interesting triangle, don't you? See, the tube height is one side of the triangle, and then how far it goes in a certain period of time is another side of the triangle, meaning half the speed of light times the time you're looking at it. Maybe 2 seconds. Maybe you're only watching this thing for 1 second. Let's keep it really simple. For 1 second. So you've got the flash of light moving up the tube according to us. We don't see it actually make it to the top of the tube. Why not? Because it's 1 light second long and the flash only goes so far. It goes 1 light second. It does travel at the speed of light, but the clock appears to be running slower because it doesn't make it to the top. Some of the clock speed is being allocated to move through time. All right, so we can take the length that it's going, the speed with which it's going, times the time we're watching it for. Doesn't matter how long we're watching it for. But we know inside the tube, they have their clock. And they see the light pulse going up and down at the speed of light times the time that they're watching it. So how does this time convert into the time that we see from the outside? Well, it's just simply the Pythagorean theorem. So you got the speed of light times the time that we see it to go, which is the hypotenuse of the triangle, and then we have the speed with which the tube is going across our line of sight, or towards us or away from us, and that's going so far and so fast. So we have that speed times that time, which is a distance squared, and then this distance, which is the inside the clock that the person riding with the clock sees. So that speed is the speed of light times their clock time. squared. So that's Pythagorean theorem. And we find that if we do the algebra, that the actual time difference that we find is that the clock speed, the clock time that we measure outside is longer than the time is longer than their time inside. So the time, there's a difference between the two times, and we on the outside see the clock moving by, going slower. Now it's relative. So if you were in the clock tube, with the clock tube looking out, you would measure the exact same thing if they had a bunch of clocks that you were rushing by. That's really fascinating. So this is not some trick. Remember, it's relativity, so you see things both ways equally. So if you are stable and steady and everything's rushing by you, you see them moving slowly. Their clock's moving slowly. And everything, every aspect, every clock, biological processes, movements, you drop something, it seems to drop slower. You throw something, it is measured by you outside to be moving slower. Heartbeat rates are slower. Anything that could possibly be used as a clock is moving slower. Therefore, time rushes slower by, as when you look at an inertial reference frame that is moving by you. Inside that inertial reference frame, it's moving slower. That's a very counterintuitive thing, but it's all a result of the constancy of the speed of light. All right. And our third thing is that the length of the room that's rushing by is shorter. So let's go back to our original idea that we got a room filled with clocks, and we've got a room full of clocks, and it's rushing by us. And so I've set everything up. I jump outside. I watch the room rushing by. I see that actually the room must compress. In fact, it does compress as it moves by. The room is shorter in the direction of motion. Well, why is that? I mean, that's kind of weird. And that's because everyone has to agree on measurements. Everyone has to be able to predict each other's measurements. Because if I'm watching that move, it's the same as if they're in there watching me move. So the relative speed is the same no matter who's watching that. So we've got a stationary thing. That's me thinking I'm stationary, and the clock is in the room with the clocks is moving by. Or if you're in the room of clocks and you're looking outside and watching somebody else, and you would think they are moving by. It's just in a negative direction, So the speed is the same, but it's in a different direction. So the effect must be the same. So you measure the distance, a speed is measured simply by some length divided by some time. And so no matter how you measure it, it's always some length divided by some time. And that speed is the same for both because it's a relative speed. So the person's measuring rulers, let's say, I got a ruler, I'm going to measure how big that looks when I'm looking at the window. So the distance, we already know that the clock times are different. So in order for the speeds to be the same, then the distances must be different. And so therefore the distance must be different because the speed must be same. It's just a change in distance divided by a change in time. But we already know the time is different and the speed is the same. So therefore, for the other observer, we must see that the length of the clock, the distance must be shortened by the exact same rate that the time is lengthened. So this is a really interesting set of parameters. So everybody it has to be mutually exclusive. You can't gain time by going from one place to another. You can't lose time by going from one place to another. The relative speeds are constant. That's the first postulate of special relativity, is that inertial frames are equal, and that I'm an inertial frame, you're an inertial frame. So the speed with which they're going relative to each other says it's just a length divided by a distance, a length divided by a time, and a length divided by a time. And everybody measures that. We already know the times are different, so therefore the lengths have to be different in order for the speed to be the same. That is because of the central axiom of the first axiom of special relativity. We're keeping Galilean relativity, that you can't tell that you're moving. You're in an inertial reference frame. So this is kind of weird, ain't it? And so it's a necessity of it that if the speed of light is a constant, no matter who's observing it, time is slower. The length that you measure for a moving reference frame is shorter. That's foreshortened in the direction of motion. The clocks are out of sync. So this is a big bunch of statements. Is it true? All right. Is it really, really, really true? Well, okay, Rossi and Hall in 1941 were doing work on cosmic rays. And so there are particular kind of cosmic rays, which are high energy protons or high energy nuclei that hit the Earth's upper atmosphere. And when they hit the Earth's upper atmosphere, they basically hit other atoms that are in the Earth's atmosphere. And that creates, because it's a very energetic collision, it creates other particles, other subatomic particles. It can create electrons, it can create neutrinos, but specifically one of the particles that's created are called muons. And muons are kind of like electrons, except they're a lot more massive. And because they're more massive, they're unstable and they fall apart and break down. So muons, therefore, have a very short half-life. We don't see a lot of muons around here. Nobody gives you you can't go to the bodega and get a muon sandwich. So muons don't live very long. In free space, they live about a 1.5 microseconds. So that's kind of a very short lifespan before they break apart and decay into other products. So but then they have a specific mass, and they have a specific charge. So you can measure that if you can catch them. You can say, oh, I'm getting this amount of charge. Oh, I'm getting this stuff. I'm getting hit by this kind of mass. So we can measure that, et cetera, et cetera. So you can measure how many muons arrive at your detector. So let's say you're down on the ground at sea level and you have a little muon detector. And you look at them and you say, wow, I'm getting thousands of muon hits per second, maybe a few hundred hits, whatever it is, a few hundred hits of muons per second. Here's the thing. Muons live only a microsecond, right? So if time dilation did not occur from us watching the muon travel to us, because where do they get formed? They hit the upper atmosphere of the Earth, which is about 20 kilometers up or 12 miles up. Let's just call it 10 kilometers or so, right? So let's say it's about 20 kilometers or 10 kilometers, somewhere very high up. It so happens that the rate of decay is exponential. So half of them will disappear in a half-life. So the half-life of a muon is about a microsecond and a half. So it takes about so how far does it travel inside of that time? It travels about maybe 500 meters. Great, 500 meters, right? How much is 500, maybe 400 or 500 meters compared to 10 or 20 kilometers? That's a lot. So you could say, well, if we say these are 20 kilometers, call it 500 meters, it's 1, 20, 40. So it would be reduced, there's 40 of those lengths between when it's first created and how far it would go. So it'd say half of them would go away after one length, right? So you might make a whole bunch of them at the top. One length later, 400 or 500 meters later, you expect to have half of them remaining. 500 meters after that, you have half of those remaining. And 500 meters after that, you have half of those remaining. And you do that 40 times because remember, it's 20 kilometers. It's a half each time. So you have 2 to the 40th less at the bottom. So let's say you detect 1,000. Let's say you detect 1,000 of them. To get 1,000 at the bottom, you would need to create 2 to the 40th times 1,000 to get there. So that's a huge, well, it's actually more than that. It's much larger than that. For every one that you get, it had to have been the 10, wow. So to get one, that means you left behind 2 to the 40th, which is a huge number to leave behind. So because we actually get hundreds and thousands at sea level, therefore the time must be delayed. Why? Because their clocks move slower because when they're created, it's such an energetic reaction that it takes a very short period of time, about a microsecond, to get from the top of the Earth's atmosphere to the bottom. That's what we see them to be. We see their clocks foreshortened. So therefore, instead of getting the expected 0 number of muons, because they should disappear in the upper atmosphere, they should just simply go away. But we get them at sea level. 2 to the 40th is a big quench. It quenches a lot. So we get them. So therefore, their clocks are running slower. All right. So that's kind of a weird thought. Let's say let's use this special relativistic concept and say, let's say we're riding along with the muons. And why I said Rossi and Hall is they actually devised this idea and measured it. So that's pretty cool. And then you say, let's now devise the idea that what does it feel like to ride along with a muon? Well, if you're riding along in a muon, you don't have an extended bunch of clocks and you can't see the clocks. But what you can see is that you arrive at the Earth. All right. So you see, instead of seeing 400, but you only go 400 meters or 500 meters. Remember that in your clock time frame, you live a microsecond and a half. And so you can only go that 100, 500 meters before you fall apart. That's your life. So therefore, the atmosphere appears to be compressed in the direction of motion. So the Earth itself appears to rise up at you faster because the distance between where you were born and where you hit the Earth is shorter. So that's how it works out. So from our perspective, looking at the muon, its clock, its internal clock, how long it lives is apparently longer. And from the muon's perspective, it has its own internal clock. It says, I'm only going to live a microsecond before I pop. But yet that microsecond, because it's moving so fast, or more specifically, the Earth appears to be rushing towards it. In fact, the Earth is, remember, it's a muon. It says, I'm at rest in my reference frame. So the Earth is rushing towards it. That's relativity. That's the first postulate of special relativity. The Earth is rushing towards it. So since the Earth is rushing towards the muon, it seems to be rushing so fast that the distance between it when it was born and where it hits the Earth is only about 500 meters. So that's an amazing, amazing set of things. There are numerous other experiments that show these results from special relativity. Special relativity is so well established that it is no longer it's considered completely settled science. It is used as part of the definition of the meter. We no longer measure the speed of light. All those experiments that we heard about the measurement of the speed of light, they're irrelevant now because special relativity says that it's simply a conversion factor between length and time. That's all it is, which is really something. So special relativity is extremely well established, and it's a basis for many of our scientific uses. And in fact, we've replaced, no longer worry about the length of something, we worry about only the measurement of time, because we convert it to length by defining the speed of light. The speed of light is a definition. All right, so next time we'll take it a bit further and see how this merges in with gravity. See you soon.